Okay, so today we're going to be talking about solubility and how things dissolve, and the term solvation, some new vocabulary words. Try to get your mind around what's going on in solution. We'll review the solubility rules from Gen Chem 1, like on strong electrolytes and precipitates and those kinds of things. And then we'll use the concentration units in a mass action table. So I've got some blank ones here. I'll pass those out when we start that problem. Okay, so essentially, we could go into much more detail on what's going on in solution and so on, but this second semester of chemistry is really computationally heavy, and so at each lecture, if I get a chance, I'm gonna work problems for you. I'm gonna try to get you comfortable with working problems, because that's the thing you need the repetition for. You know, if you can understand the concepts by reading the book about solubility, that's fine. You can learn those concepts. It's sometimes doing the problems that we always get feedback. I wish you did more problems in class. And so we're going to be doing one of those problems. So we're going to introduce the concentration units today and then immediately start using them in a problem. So let's talk about what's going on with solutions. Solutions are homogeneous mixtures of two or more substances. So in a solution, a solute is dispersed uniformly through the solvent. Now, we typically think of solute and solvent as something that dissolves in a liquid, but solutions can be any homogeneous mixture. So the air we're breathing is a solution. It's a homogeneous solution of nitrogen, oxygen, argon, CO2, and water. You could have oxygen dissolved in water. That's how our fish survive. Okay, so they're filtering that water through their gills, and their gills are pulling the oxygen out. So that's a solution. The water gas is dissolved in the liquid. Ethanolic drinks are alcohol dissolved in water. So there, the state of the solute and the state of the solvent are both liquid. You can have salt water, you can have all kinds of things. You could even have solid solutions, and you probably have some in your pocket. I've got one here. This is zinc and copper. So this brass key is a solution. It's a homogeneous solution. And how do you tell the difference between a solution and a substance? Right? This is zinc and copper, but it's not a compound. It's not a substance, it's a solution. It's a solid solution. What would make it a compound?
If one of the elements was completely separated from it?
No, but you're on the right track. We're thinking about the elements. So we have zinc and copper in here.
Yeah, you can't separate those easily. I mean, that ring that's connected to it.
Yeah.
If that was considered part of the key, then that would make it a compound, right?
They'd make it heterogeneous, because there'd be identifiable things that were different. So if I took a little scrape out of this, I would have a certain percentage of copper and a certain percentage of zinc. Okay. But remember, it's a percentage. Can I change that percentage by, say, 5% and still have a brass key? Yeah, absolutely. So a compound has fixed compositions, like H2O. It's always two H's for every O. That's a compound or a substance. Okay, it's not a mixture of hydrogen and oxygen. It's actually a compound. So solutions have variable concentrations. So write that down. Solutions have variable concentrations. And compounds have fixed concentrations, like water, like H2O, right? Compounds. I'm going to draw a line here. Compounds. Okay, so I put H2O in there to illustrate a compound. Okay. So you can have a copper heavy brass that looks a little bit more orange. Then you can have a copper light brass, a more zinc heavy brass that looks a little more silver colored. So you can blend those at different proportions. They're definitely a solution. It's just a solid solute and a solid solvent. Okay. Let's talk about aqueous solutions. So when we take a crystal, like in this case, a salt crystal. Oh goodness, let me turn my phone off. Excuse me for that. Okay. If we take sodium chloride crystals, a nice little cubic crystal, and stick that in water, these are ion dipole interactions. The sodium ions, the cations, will be surrounded by the water dipoles, and the chloride anions will be surrounded by the water dipoles, and they will pull that apart. And so it is a competition between forces. So what's holding the sodium chloride crystal together is the Coulombic attraction, the pluses and minuses of the sodium and the chloride anion and cation. So they're connected by positive and negatives being attracted to each other, and they snap together and make that nice cubic crystal. And water is attracted to water because of the hydrogen bonding. And so these two things would not mix if the water didn't like chloride ions and the water didn't like sodium ions, but water does like chloride and sodium. So when water gets one chloride off, it surrounds it, and now 6 water molecules can be around a chloride and 6 water molecules can be around a sodium. So we can make a whole bunch of new connections in solution than we could make before we have the solution. And so it's this competition. And there's really no way to know, predict if something's going to be soluble or not. Our best guide is like dissolves like, right? And so we just have this competition between forces. And so we'll have the solubility rules in a minute that sort of tell you which kind of substances dissolve in water and which kinds don't. And if you wonder why, it's all because of this competition. Which side wins out? The solution wins out, or the individual solvent and solute stay separated and they individually win out. So let's look at how the solution forms. So you can notice that this beautiful little cubic crystal has been torn apart. And so some of those sodium ions have been surrounded by the water, and the chloride ions have been surrounded by the water, and the crystal's dissolving. And so here it's completely dissolved. And now you see that the solute particles, and in this case, these are ions. So this is a chloride ion, a Cl minus. No, that's a sodium, sorry. Let me erase that. That's a sodium cation. And this is a chloride here. And water is the solvent, and it has gone around those and clustered around those particles. And so that's what we call solvation. So the solvent is doing something. It's solvating the ions, and it's coming around and latching onto them. And all of these associations here are lower. Oh, bless you.
Thank you.
So these are lower energy situation than this, right? If the crystal was the lowest energy, it would just sit there and water couldn't break it apart because it would be going uphill energetically. Just like you set a ball at the bottom of the hill, it doesn't just roll uphill spontaneously. You set a ball on the side of the hill, it's going to roll down spontaneously. So this crystal, you put it in water, it's not at the bottom of the hill. Pulling these ions off, making lower energy structures, that's downhill energetically, and it will roll downhill spontaneously, and this thing will mix. And so that's what we have. That's solvation. Any questions about the concepts of what's going on? This is in particular, this is for aqueous solutions. We're dissolving things in water. Okay, there's different types of solutions. This is a saturated solution. If we put too much salt in the water, it will solvate everything it can, but eventually you're just going to have salt crystals in the bottom, and you're going to have sort of it's a dynamic equilibrium. So some of it, like this chloride may come off, and then this chloride bumps into that crystal and then snaps back on. And so you have these ions coming and going onto the crystals, and some will leave at the same rate, others will deposit. And so that's what you have with a saturated solution. We've got as much solute as possible at that temperature. Now, back, I don't know, several lectures, I had the thermodynamics equation of mixing on there, and it had temperature, and temperature was next to the entropy term. And so we can drive more into solution by raising the temperature. So you might have a saturated solution, you could raise the temperature and get it all to dissolve. And that's how we make our really, really sweet tea, is we dissolve that sugar in hot water, and then at cold water, it's actually super saturated. It's got more sugar in it than it should be holding. Yeah. So this dissolved solute is in dynamic equilibrium with the solid solute particles. Okay, if you have an unsaturated solution, it could hold more, but you've just run out. It's all dissolved. And so unsaturated solutions have less than the maximum amount of solute for that temperature. Okay. And then this supersaturated solution. If we dissolved all of the solute in a hot temperature and we cooled it down, we have an unstable situation, right? We've got way more solute, and it just hasn't paired up and started making crystals. And so all you have to do is just drop one little crystal into that solution, and it will rapidly form crystals. And so this little seed crystal is dropped in, it hits right here, and immediately starts growing crystals. And once that process happens, it will start growing crystals everywhere. And so that's a seed crystal. You can also scratch the side of the flask, and that's a really common thing when you get into organic. When you're recrystallizing something, dissolve it in a small amount of solvent, warm it up so you dissolve it, and then let it cool down, and then you start scratching the side of the beaker, and crystals will start crashing out of solution. So it's just that the vibration of the glass, and then the small amount of friction. You know, it's kind of like you're scraping the solvation shell off and letting those ions find each other, or those molecules find each other. And once you get a couple of pairs to join, then the others can stick to that. And so we just got to get it started, and then it'll start growing the crystals. So it's pretty fun. This is how the hand warmers work as well. So they will dissolve something in hot water, then cool it down, and then it's like they stored that heat in the substance, and it's in solution. And sometimes you have a little disc in there that kind of acts like a seed crystal. You flex that disc, and it starts the crystallization process, and it starts to grow those crystals, and it's exothermic, and it releases energy while those crystals are growing in those little hand warmers. Different kind of hand warmers are made differently. Others are like they're in a plastic sealed bag, and they have oxygen or iron in there, and it will react with oxygen and make heat. But some of them are based on recrystallization. Now we talked about like dissolves like, and here we have a series of alcohols. Notice the OH groups. Okay, see all of these OH groups. And here's the solubility in water. And so this infinite solubility, that's just another way to say it's miscible. Okay. So miscible means it can be mixed in any proportion. And this right here, this hexane, we've got water and oil or fat. So we talk about fat-soluble drugs and water-soluble drugs. This is another way to think about it, oil solubility or water solubility. Notice how they all have OH groups, and they all have some carbon and hydrogen pieces. How can you explain this? Like, what's going on in this chart? So I want you to just sort of struggle with what's going on here. So they both have OH groups. They both have organic pieces. So why are some soluble in water and others not?
They have more hydrogen bonding.
They all have one OH group each. So they should have the same opportunity for hydrogen bonding.
But the CH2s are becoming more complex.
Yeah, and you can think of this piece right here. This is like, when we say like dissolves like, this piece is like water. And this piece right here, down here, this is like oil. I know it's hard to read on there. I wish I had a thicker pen, but
You put weight
yeah, so
instead of water.
yeah. So this is like oil. And so notice the more oily the molecule, the more it's soluble in oil. And the more water-like the molecule, the more it's soluble in water. Okay. And it's not an either or. This is butanol is kind of soluble in water, okay, but then pentanol is less soluble and hexanol is even less. So it's kind of a smooth transition in these alcohols. But this idea of water versus fat soluble is a huge thing in medicine. It's hydrophilic, hydrophobic. It's how we get our medicines orally, or if it's fat soluble, maybe it's not good for ingestion. It's not going to go into the stomach, so you need to inject it. So it's a lot based upon this hydrophilicity, hydrophobicity. So here's an example of the alcohols hydrogen bonding to each other. So here's the OH group aiming at the lone pairs on another oxygen. So there's those lone pairs on that oxygen, and that hydrogen is aiming right at that lone pair. And then here, water is very similar. So it's going to come along and it's going to hydrogen bond to that OH in the alcohol. So this explains the difference between, here's an organic molecule, glucose, but look at all the OH groups on this. It is a carbohydrate. Now, think about the name carbohydrate. Carbo stands for carbon, okay? And what do you think hydrate stands for? Water, okay? And so if you're going to hydrate that, then you're going to have an H2O. So this piece right here is the empirical formula for all carbohydrates. All carbohydrates have that formula, CH2O, and the only difference is the number of times they use that unit. See here, this is a CH2O and a CH2O. So this one has 6 of these units. This one on the back is a little more complicated because it's got a carbon here, an oxygen there, and then I'm going to grab one of those hydrogens and stick it on that. So, and then that one. So there's 6 of these in glucose. 1, 2, 3, 4, 5, 6. Yeah. And so it's not, I mean, that molecule doesn't look anything like water, but all those OH groups can hydrogen bond to water. So glucose is very soluble in water. And here's cyclohexane with no OH groups, very oily, completely insoluble in water. So, and these are the space-filling models. It's kind of a way of looking at the molecule where the hydrogens and carbons and everything kind of take up the amount of space that their electron cloud would take up. Notice you don't see any oxygens on this one. Water has really nothing to hook onto for this molecule. But over here, it has all of those oxygens, and those oxygens have lone pairs that the water can hydrogen bond with. Here's some vitamins, vitamin A and vitamin C. Again, vitamin A is fat soluble, and vitamin C is water soluble. You have all of those OH groups. And then here's the ionic solubility rules, those ionic compounds from Gen Chem 1. And so I just wanted to put this in here to review. mainly this top group for sure. Put a star by that one in the notes, because that's group 1 cation. So you look at the periodic table, group 1, all the way down, lithium, sodium, potassium, rubidium, etc. Those are soluble in water, no matter what they're paired with. You can put them with sulfur, you can put them with hydroxide, you can put them with carbonate, any compound, lithium carbonate or lithium hydroxide, it's going to be soluble in water. Okay, and then your halogens are mostly soluble. So chlorides, bromides, iodides, there's only a few exceptions to those. But if you have like iron chloride, it's going to be soluble. Or if you have, I don't know, titanium iodide, it's going to be soluble. But you have some exceptions. So mercury 1 and silver and lead, etc. Okay. There's a few different exceptions for fluoride. This one here, put a star by this one. This is acetate here. Acetate, bicarbonate, nitrate, and chlorate. Notice no exceptions. Those are soluble no matter what you put with them. And then sulfates, they're mostly soluble, but there's quite a few exceptions for the sulfates. If you look at, there's a lot of 2+ cations that sulfate precipitates with because it's an SO4 2-. Look at barium, calcium, they're all in that second group. So barium, strontium, calcium, those are going to precipitate with sulfate, but magnesium and beryllium will not.
So sodium bicarbonate is super soluble.
Exactly.
Okay.
Yeah, super soluble. Okay. And then down here you have these insoluble. If I pair it with a carbonate or a chromate or phosphate or sulfide, it's probably going to be insoluble. The only way to get these anions in solution is to put them with a group 1 cation or ammonium, right? And you know that those would be exceptions because those are starred. Those are soluble in anything, right? So even these insoluble anions, you can get into solution if you pair them with something in group 1. Okay. And then hydroxides too. So hydroxides precipitate out unless they're group 1 hydroxides, and then barium also will dissolve. A barium hydroxide will dissolve. Okay. So I just wanted to go through these one more time, put them in the notes so you have an easy reference to them, because we'll see in our reaction that we're going to do today that we have a precipitation that takes place. And so how would you know that unless you looked at these solubility rules? And it's going to be silver chloride that precipitates. So yeah, chlorides are soluble, but one of the exceptions is silver. And so, okay, so let's talk about how we express the concentrations of solutions. So we have a solute that's dissolved in some other substance that we call the solvent. So we could do percent by mass. And so we could just take the mass of A in solution divided by the total mass of solution times 100%. So that's pretty easy if we were weighing things out. And this is very easy to do on a balance. You just take your beaker, you put in whatever solution you want, write down the mass, and you can even add your solute right to the beaker and look at how it goes up. And take difference to know how much you added, and then divide by the total, and you've got the mass percent. If it's a really dilute solution, in other words, you didn't put much mass in at all, you might be working with parts per million of A or parts per billion of A. So that would be the mass of A in total in the solution divided by the total mass, and then times that 10 to the 6th parts per million. Or if you're doing parts per billion, it's times 10 to the 9th parts per billion. And remember that it's just like multiplying by 100%. And this percent piece is the same as the parts per million piece, right? And the 100 is the same as this 10 to the 6th, right? So a lot of people freak out when we get to parts per million, but it's no different than percent. It's just for smaller numbers, okay? So it's like parts per million is a unit, like percent is a unit. Let's look at mole fraction. We've done that one before. Moles of A in solution divided by the total moles in solution. So you would need to know the moles of the solvent, the moles of whatever you put in there. Add that together. That's the total. And then you just put moles of A on top, and that's the mole fraction. And then let's talk about the one that we're going to use the most in the middle part of the course, and that's molarity. So it's back in chapter 4 of the book. It is a bit tricky because it's temperature dependent. So if you notice on all of these volumetric flasks down here, it has TC, which means to contain, and that's in contrast versus to deliver. Okay. What is the difference between to contain versus to deliver? This mark here, when I fill this solution up to that mark, this is 100 milliliters inside the container. But can this container accurately deliver 100 milliliters? No. How am I going to get every little bit out? There's going to be one drop left in the inside, right? So this volume mark is marked so that it can contain 100 milliliters exactly. Okay, and then you would pipette out of it or put it in another container to use it. But this is just the difference. That TC means to contain. If it was to deliver, like on a pipette, some of these volumetric pipettes say to deliver and 50 mils or something like that, and you let it go down and it is delivered 50 mils to your flask. If you look in there, there's a little drop still inside the nozzle. Don't blow that out. It's meant to deliver and leave that little drop in there. It delivers 50 mils, and they've taken into account that extra little a bit that should be in the tip. Okay, and then it has the temperature here, 20C. So this is calibrated to be 100 milliliters. I'll do it over here at 20 degrees C. If I warm it up, then the solution's going to expand, and that mark would have to be in a different place if it was at a different temperature. If it was supposed to be at a colder temperature, I'd have to draw the mark lower on the neck. And so they calibrate this. They put, a calibrated amount of liquid in there, and then they get it exactly at the right temperature, and then they etch that line. And so if you look at these flasks, those lines are all in slightly different places because the geometry of the little bulb down at the bottom is slightly different. They blow these out of molten glass, press them into shape. Okay, so this would be the liters of solution right here. So this would be 0.100 liters of solution. And then if I were making up a volumetric concentration, I would weigh out some of my solute, put it in a little watch, in a little weigh boat. So I've got my little powder here. I fold it over, I drop it down into the flask before I put any liquid in there, because otherwise it'll stick to the side of the wet glass. Then I pour the liquid in. I fill it up to about, halfway and stir it until all the powder's gone. Okay, make sure it's homogeneous, and then I dilute up to the mark. So then I fill it up here, and I stop right there, let it all, come to equilibrium so the temperature's not changing a little bit, and then I come up with the last little bit with one drop at a time. And so then it's very accurately made into 100 or 0.1 liters of solution. I know how many moles of substance I put in, and so I have my molarity. So molarity is a capital M or uppercase M. not mega. Okay, so you have to use context to know when the capital M is mega, like megajoules, okay, or when it's molarity. Okay, so you've got to pay attention. Is the problem talking about a concentrated solution or not, and so on. Okay, molality is a lowercase m. Not meter or mass. We've used M for a bunch of different things in this class already, and so you just got to use context. This is a concentration unit. It's mole of solute per kilogram of solvent. So notice this is different. This is not solution. This is not the total solution. This is very nice because masses are not temperature dependent. So I can use a balance for all of my concentrations. And I can put my beaker on there. I can pour in the liquid so I know how much solvent I'm using. Your balances sometimes don't do well if you've got solutions that are evaporating and so on. So you might put a watch glass or cover over that so that you can get a good accurate measurement of a stable measurement of a liquid. Then you can put your solute in there. You know how many grams you put in. You know the molar mass, hopefully, so then you can convert to moles. So moles of solute per kilogram of solvent is molality. It's kind of hard to say, so I always emphasize it, molality. And you can't convert from one to the other, but you need to know the density of the solution. So I think this might be the last slide in your notes. So I've done some calculations from here to calculate the conversion from molality to molarity. It's fairly involved, so I wanted to show it to you. Okay, so molality is moles of A per kilogram of solvent. And I color-coded this for you, okay? So if you have the little 4-color pens, that'd be great. You probably should go get one for us. Okay, and then molarity, down at the bottom, molarity is moles of A in liters of solution. So this kilogram of solvent to a liter of solution is something that we've got to fiddle around with. We've got to figure out how to get from one to the other. So we can calculate the mass of A because we're going to want to get out of this kilogram of just the solvent and add in the mass of solute that we put in. So I want to convert the moles of A to grams of A. And then I want to add that in. I'm going to go ahead and make it kilograms. And I'm going to go kilograms of A plus kilograms of solvent equals kilograms of solution. So now I've got the mass of that solution. Everybody see what we did? We had the mass of the solvent. And how much does the whole solution weigh? We've got to add in the mass of the solute. So we get those two masses, add them together, we have the solution mass. So we must know the density, though, to get from kilograms here, this thing right here, down to volume. So mass over volume is density. So a lot of times we assume the density of water applies. So that's the missing piece in a lot of these problems. If it's a dilute solution, something that's not very concentrated, then this assumption can work. Okay, so we have kilograms of solution and 1 liter solution of water. If this solution is essentially the same density as water, 1 kilogram of water is 1 liter. How do I know that? Well, water is 1 gram per milliliter. Okay, if I multiply both of those by 1,000, I get a kilogram. 1,000 milliliters is a liter, so they're the same thing. And so that converts this kilogram of solution. If I assume the solution is essentially water, then I end up with this liters of solution. And so then that goes right down here. Now that fails at high concentrations, but if you were doing this problem and you were telling me how you proceeded, you could say, assuming the density of water right here. Okay. So let's use concentration units in a mass action calculation. What happened? Okay. They need, when y'all are done, they need to come over there. Okay. Okay, so this is the reaction we have at the top. You can write out your balanced chemical equation. We're mixing an aqueous solution of aluminum chloride, which is AlCl3, with silver nitrate, AgNO3, aqueous. It's going to make silver chloride solid. It's going to precipitate out, and we're going to have some spectator ions left over, aluminum nitrate, aqueous. Okay, so I had the 3 chlorides in the aluminum, so I needed the 3 here for the silver chloride. All right, and that means I need 3 of these silver nitrates. And so I've got 3 nitrates, which is fine because that pairs up with the aluminum 3+. So everything all works out with the 3s in front of the silver nitrate and the silver chloride. So this is why we want to go back to the mass action table to show you where these concentration units are going to show up. They're going to show up in converting from lab to chemical units and from chemical units back to lab units. Because what do we measure in the lab? We were measuring masses with balances, and that's easy. You get the molar mass out the periodic table. This now is not so easy. If I get a volume, if I give you 20 milliliters of something, you got to know how concentrated it is. And that's where the concentration units come in. If you don't know the concentration, you're out of luck. Thank you. So let's do one. We've got 20 milliliters of a 0.2 molar solution. So, off to the side or on the back or whatever, let's calculate how many moles of aluminum chloride we have. So we have 20 mils times 0.2 moles of aluminum chloride. Okay. And so I'm going to do these problems in millimoles. If you look at this, the liters or the volumes have canceled. I've got this little milli still here, and so I'm going to leave that because that's real easy. If I have 20 times 0.2, I have 4 millimoles. I could just as well get rid of that milli and make it 0.004 moles. But I would like for you to get comfortable thinking in terms of 1,000th of a mole, because a lot of times in our regular labs we deal with pretty weak concentrations, and millimoles is a good unit of chemistry to use. Okay, so once you're finished with that calculation, you can write it in that square right there. Okay, so that's how many moles of aluminum chloride we have. And that's our initial chemical unit for that part of the problem. We could do the same thing for this other, for the silver nitrate. We have 2 times 0.3, which gives us 6 millimoles of silver nitrate. And notice down here, this is what I'm interested in. I'm interested in the mass of the silver chloride that precipitates out. I've got two reactants in my equation and I've got two amounts, and so I've got to figure out which one I'm going to run out of. So this is a limiting reactant problem. Okay. And so we've got to do the math to figure out what X is. So I should draw this on a post-it note to show you. Do this calculation off to the side. So 4 minus X equals 0. What I'm doing is I'm saying, what if I ran out of this one? What would X be? Well, X would be 4 if I ran out of my silver chloride. What if I ran out of the silver nitrate? I would have 6 minus 3X equals 0. In that case, X equals 2. You've got to go with the smallest X. That's your limiting reactant. So I'm going to run out of silver nitrate before I run out of aluminum chloride. I'll pause there in case you have questions.
Does that always work?
Mm-hmm. Every time. And it works for kinetics too. As we bring X from 0 up, we can see how everything on the table changes. So if we make X 0.1, we could put 0.1 in there and we could see how everything is lost a certain amount and a little bit is grown over here, and then X goes to 0.2 and everything more is lost on the reactant side and more is appearing on the product side. And that's what's happening with kinetics. It's sort of, as time goes on, X is growing. And when it hits 2, we're out of something and the reaction stops. Yes?
Just to clarify, the 6, it came from 6 millimoles, correct?
Yes. Yeah. So the 6 is connected right here. Yeah. So now we know X for the whole table. And so we can put it in there. I went ahead this time and wrote it in for X. So we have minus 2 millimoles in the first column, minus 3 times 2 millimoles in the second column, plus 3 times 2 millimoles in the third column, and plus 2 millimoles in the fourth.
So we're going to do more practice with this, correct?
Yeah, this is just, I hit this drum a bunch throughout the whole semester, yeah. The reason I like this is because this is a way to solve for everything on the whole reaction instead of just one path through it with stoichiometry and the little trains of parentheses. If you know really where you are and where you want to go, that's faster. But in terms of teaching, I'm sort of showing the steps. It's still the same steps. We get out of volume into moles. We go from moles through the X's, that gives us our mole ratio, and then we do the last bit, which will be the lab units. So we've run out of the silver nitrate. So 6 minus 3 times 2. So 6 minus 6 is 0. So let's calculate this one. So 4 millimoles minus 2 millimoles gives us 2 millimoles left over of the aluminum chloride. Does everybody understand that piece? Right? This is the excess amount of aluminum chloride. Okay, we started out with 0 millimoles of silver chloride and 0 millimoles of aluminum nitrate. And so we're going to end up with 6 millimoles of silver chloride at the end and 2 millimoles of aluminum nitrate. So that's pretty easy. Boom, boom, boom. I've got the whole, everything in the final situation. So the amount of silver chloride is really easy because it's a mass conversion, right? We just look up the molar mass and we can calculate that, right? It's 6 millimoles, which is 0.06 moles. There's our conversion from 6 millimoles to 0.06 moles. Times the molar mass, 143.5. So silver, find it on there, it was 107. I thought it was 108, yeah, 108 plus 35.5. And so we get the 143.5, and we end up with 0.86 grams of silver chloride. Notice how we didn't have to deal with any volumes because it's a precipitate. That's how much mass precipitated out. It's the next calculation that is the one that catches everybody unless they're really careful. Okay, so are you careful? You're awake? All right, it's the next one. What's the concentration of aluminum nitrate? We have 2 millimoles here, and you've got to divide it by the total volume. And the total volume is everything you mix together. So the volume of our solution is now 40 milliliters, and that's the thing that messes everybody up. The total volume of the solution changed when we mixed these two solutions together. So we put 20 mils of this and 20 mils of that together. Now the total volume of the beaker is 40 milliliters. So we have to divide by that total solution amount, and that gives us 0.05 molar, that's the concentration, 0.05 molar aluminum nitrate.
So because you had millimoles and milliliters, that's moles over liters.
Yeah, that's right. And so it works. That's great. Thank you for pointing that out. So I have millimoles and milliliters, and so I can just leave it in milliliters because these two millis cancel. And I have moles per liter. Okay, so let's do the other ones. So that's 0.05 molar aluminum nitrate. Here's 2 millimoles of aluminum chloride, again in 40 mils of solution. So we end up with 0.05 molar aluminum chloride. And then the concentration of the aluminum nitrate is 0 because we ran out of that. So we filled out the whole table. There's nothing I can ask you about this system that you can't answer. Yes?
Can you show the equation to calculate the molarity of aluminum chloride?
There you go. Yeah. So we have whatever was left over was that 2 millimoles here. And then again, divide by the total solution volume, 40 mils. Okay, so let's just look to see some of the things that we see here. Notice we started out with 4 millimoles here of aluminum. So let's follow the aluminum for a second. And after the reaction, we have 2 millimoles down here. But we also have 2 millimoles over here. So the aluminum hasn't been lost, it's just moved around. So it still adds up to 4. The silver, okay, we came in with 6 millimoles of silver. Okay, we have 0 here, but it's over here. So it's all moved over to the silver chloride. Okay. What about the nitrate? Well, we had 6 millimoles of nitrate. Here it looks like we have 2, but notice there's a 3 down here. So 2 times 3 gives us the 6 millimoles of nitrate. So that's cool.
For the silver nitrate at the final lab unit, it's not supposed to have the 3 subscripts at the bottom.
Oh, wow, thanks. Yeah, it was a copy-paste error. So scratch out this piece right here. Thank you. I was trying not to make those. And sorry, yeah. Did you find another one?
No, did you say scratch off the 3?
Yeah, leave it should be just AgNO3 without the parentheses and the extra 3, okay? Yeah, and so then the only last one is the chlorides. Look here, 4 times 3, so I have 12 millimoles of chloride, all right? I have 2 times 3, so I have 6 millimoles here, and I have 6 there. So that adds up to 12. So everything all balances out. It's just a nice, beautiful thing. I know where all my atoms and masses and millimoles went. Okay, y'all. Thanks for your attention. Y'all hung with me the whole time. That's good.